Hi there. Oh, I'm not feeling too well, by the way. After I did that last video, I ate some chicken, and within 10 minutes it all came up. I've been lying on the couch with a really bad tummy, with stomach cramps. Anyway, I'm not feeling 100% yet. I don't know what happened there, just didn't react very well to it at all. Right, so I'm going to quickly look at this star, a 4-wire star connection. So that's why that video took a wee while to come up, by the way. Because I just clicked it on a wee while ago once I managed to get myself off the couch. Right, anyway. Right. Let this star. Wait a moment. Right, so we've got a star connection here. And this is your neutral. You've got line 1, line 2, line 3. Line 1 being 240 volts at 0 degrees. 240 at minus 20 is line 2. And 240 plus 120 is a line 3 there. Right. So whenever you do these kind of things, as long as you stick to one and work your way around in the same direction, you should always be fine. So it doesn't really matter where you start. So what we're going to do is each one of these is going to be a different impedance for L1, L2, and L3. We're going to work out the current whatever we can find for each one. And right, see if you've got a balanced star. All these meet at this point, and in an ideal balanced star, these are all the voltages and the currents are all going to cancel each other out. So you should be left with 0 at this point. It's like an earth. It's like an earth our neutral point. Anyway, so you could really draw that like that, I suppose. But the fact is that we very rarely come across balanced star circuits, and they're usually off balanced or unbalanced. And what will happen is you'll get a neutral current that will come out of that. Okay, so we're going to quickly have a look at this. So we'll call this R1, R2 and R3, say, right? And the thing is, so what we're going to be using in the star, we'll be using the 240 volts. It's line to neutral voltage. These are all lines, and this is a line, so L1 line to neutral. Right, it's important that when you look at a delta, you'll be looking at the line to line voltages, and that's where this 415 comes from. And what that is if you look at a line, see this one here, line 1 minus line 2 would be the voltage between these two. That's, even though they're both 240, it works out at 415. How can that be? How can you add two things together or subtract one in it? So I'm subtracting that from that one. Yeah, but yet I'm getting 415. It's because it's a vector addition. That's what's happening here. And a vector addition, so let's have a quick look at this. I'm just going to rub this out. I'll maybe redo it in a wee minute. Line 1 minus line 2 is going to equal 240 at 0 degrees minus 240 at 120 degrees, or minus 120 degrees. And that's the one that's lagging this one by 120 degrees. Right? And then turn these into the rectangular coordinates that I was talking about earlier. That's got 0 degrees there, so that's all going to be all cos there, 240i plus 0j. And then we're going to subtract this one, which is 240 times the cos of minus 120, and that works out at minus 120. And then we're going to, that's for the I part, and for the j part, 240 at minus 120 is minus 207 j. Remember that's 240 cos minus 120, and that's 240 sine minus 120. That's where we get these two from. I'm sorry about this. Unbelievable, I don't know what's going on here. Right. So we just simply add these. So that's 240 minus 120 is going to be 360. Then minus that's going to be plus 207j. Right. Aye. So if we want to find the magnitude and angle of that, it's going to be the square root of 360 squared plus 207 squared. Oops. That's it, 415. And the angle is inverse tan 207 divided by 360. That's 30 degrees, that works out. So that's the difference between line voltage, line to line voltage, and line to neutral voltage. Deltas are generally, they're always line to line, and star, that'll be line to neutral. Okay? So line to line neutral, line voltage line to line is equal to, and there's something, see if you, I'm not going to get into this, but 240 times what becomes 415 root 3 times the voltage line to neutral with a phase of theta plus 30 degrees. That's the equation for converting line to neutral to line voltage. Root 3 and 30 to the phase. So and now this is what I was going on about with the, hey, see if you're doing your phasor diagram and you've got this here, this and this, and see that's your lines. Now if you get your line to line voltage, it's going to be kind of like that. Oh, so it's actually like that, actually, straight down. It makes more sense because you're not, if you're using your delta, you're not going to be using your line to neutral voltages, so you kind of just disregard them. But what is handy though is if you rotate that down and use that as your reference voltage, and you can, as I say, you can kind of forget about your line voltages when you're doing a star list, as obviously, and you're looking at your line to line voltages. Just use this as your reference voltage. It'll all become more clear as we get into this. But as I say, I'm just doing the wire, the 4-wire star just now. I don't even know if I wrote down the it's quite difficult to see if there's a glare coming through there. I hope you can see that. It's not ideal. Where were we? Right, we've got a Z1, a Z2 and a Z3. Right, we'll just call it, for instance, 50 ohms at an angle of 30 degrees, 100 ohms at an angle of 50 degrees. I will say 75 ohms at minus 20 degrees or something like that, right? So you can see that, so that's 50 ohms minus 30 degrees, 100 ohms, sorry, that's 50 ohms at 30 degrees, 100 ohms at 50 degrees, and 75 ohms at minus 20 degrees. There. You can just about see that, I think. Right. And now we're going to, yeah, I'll do the calculations over here. So we've got your star connection, your L1 and your Z1, your L2 and your Z2, and up here will be your Z3 plus your L3, and of course there's 120 degrees between each one of these. Yep. Right, so you actually you kind of just treat each branch as if it's a single phase, basically. So the first thing we want to do is look at L1 is 240 at 0 degrees, and Z1 is equal to, what's that, 50 ohms at 30 degrees. Now, first thing we want to do, what's the first thing we want to do? Come on then. We're going to work out the current of line 1, say, and that's going to equal the voltage, 240 volts at 50, 30. So the current here is going to be 240 divided by 50, which is 4.8 amps at an angle of, what's that, 4.8 amps? And that's an angle of 30 degrees there. Wait a minute, that's plus 30. Sorry, this must be minus 30. I don't know why I put a minus there. Remember, when you're dividing polar coordinates, you subtract the bottom one from the top, or the denominator from the numerator. Right, so that's our first current there. The second, well, in fact, no, what we'll do is we'll just work out what the apparent power is for that individual branch there. So the apparent power is equal to VI conjugate, which is going to be that. Remember, the conjugate is going to be 4.8 at an angle of 30 degrees. So you change the sign on that, remember, to get the conjugate. So this will give us 240 times 4.8 at 30 degrees. That's 1,152 volt amps. Now, to work out the components of that. Remember, this is a vector that looks like that, and we want to work out the Q part of it and the real part of it. The Q being the reactive part of it. And again, that's just cos. Can you see that there? It's not too great. I think I'm going to do it on this doodah thing down here because it's getting a bit dark and it's quite hard to see. I've got a wee lamp thing that I can use, but it creates a glare. It makes this even harder to see at times. Right, so what we've got there then is we'll call this S1, right? S1 equals 1152 at an angle of 30 degrees. Right, now I'm wanting to find P1 and Q1. That's P1 and Q1 is going to be 1152 times the cos of 30, and that's going to be 1152 times the sine of 30. Remember, we're just doing that. That's 30 degrees there. So I'll just work that out, work that away. That's 1152 times the cos of 30. That's 997. 997.7. And that's watts. And 1152 times the sine of 30. 576. So we'll just call that 998. And that's VARs. Right. So bear these in mind. I'll just move this up a little bit and we'll do the next one. The current of say L2 is going to be as L2 times sorry, what am I doing? I'm getting ahead of myself here. Z2, which is 240 at minus 120 divided by Z. Sorry. Divided by what was 100 at an angle of 50. So that's going to equal 240 divided by 100 is 2.4 at an angle of minus 170, because when you subtract that from the bottom, that's going to be minus 50, and minus 120 is going to be minus 170 there. So if we quickly work out the apparent power is 240 at minus 120 times the current 2.4 at minus 170. Oh, sorry, it's a conjugate. Because remember, that's V and that's I conjugate, V2 and L2. Oh. So what's that working out then? .4 times 240, which is going to be smaller than the last one. 576, half actually, because it's half the current there. And the angle is going to be plus 50. Minus 20, 120 plus 150. So if we want to get P2 and Q2, oops, Q2 is going to be that's P2 cos, sorry, S2 and S2 cos 50 sine 50. See that there? That's fine. Yep. Remember, this is Q, that's That's P and that's S there. So that's going to be 576 times the cos of 50 times the sine of 50, and that's going to equal 576 cos of 50, that's what, 370, and then this other part is 576 times the sine of 50, that's 441. 441, hope you can see that. I'm going to go and get another light of some sort. Right, get a bit. Right, so L1, L2, L3, it's very difficult to see that. Oh, here we go. I'm actually going to go back to the wee thing. Right, I was just going to quickly mention something about these vectors here and the effect of the current and using the conjugate. Right, now this I1, the current 1 here, that was lagging by 30 degrees from L1. Now the next one here, we've got that at minus 70 degrees, right? So we're saying that this is up here somewhere, and there's 50 degrees from there. That's I3. Oh, sorry, I'm being an idiot. It's minus 170 from here, so it's kind of like that. I do apologise about that. That's 50 degrees, yeah, or minus 50, that's minus 120. Right, see, no matter where the voltage or the current is on this graph, what we're really interested in is the relative, the difference between the current here. We're not really interested in 170, it's more so the difference between line 2 and I2 is the key to what we're looking at here. And when you take the conjugate, what that does is it just takes into account this change here and then maps this on this quadrant here to give you your power triangle. And that's the beauty of using the conjugate. And this one here, the impedance was minus 20. Well, that's going to equal, that's going to mean that that's going to be leading this as it's capacitive by plus 20 there. Which means when it gets mapped onto it means this S1 was kind of like that. This next S2 was kind of like that. Well, smaller actually. This was much bigger than that one, twice the size of it. And now this one here is actually going to be looking like that. It might be below this here, but at least we can still add it together because it's all in this kind of quadrant here. It makes it easier actually. So this would be S1, S2 and S3. No, sorry, S2 and S3 there, sorry. No, isn't that's S3. Right, and then we want to work out what's S3 then here. We don't even worked that out yet, but we know because of the impedance. We know that the current would be leading it. So when you take the conjugate, it's going to be below this axis here. But anyway, that's going to be VI conjugate, which is the voltage to 40 at 120 times the current, which is in fact, I haven't even worked the current out yet. Right, so we've worked out S1, P1, Q1, S2, PQ and Q2. Now we're going to work out the apparent power on the third branch we work out the current first then. Is 240 at 120 divided by what was that again? 75 minus 20. That's showing that this is going to be a capacitive. That must be a capacitor of some sort, or have some sort of capacitance in it. Now that's going to equal 3.2 at an angle. Remember, minus minus is going to be plus. Sorry, minus that is going to be 140. That's can't be right. Of course, it is right because it will be leading the voltage here. Because remember, civil, C-I-V-I-L, capacitor, the current leads the voltage. So this one, though that's set at 120 degrees, if you're rotating it round this way, the one at 140 degrees is going to hit first before the one at 120. So anyway, so we've got our current there, and we're going to work out S3 now, which is 240 at 120 times 3.2 at 140 minus, remember, because that's the conjugate, so that's V and that's I conjugate, which is equal to, what is that, something like 700 or so, 800 maybe, let's have a look, see, 240 times 3.2, 768 at an angle of, you just add these, minus 20, and from that P1 P3 and Q3 is going to equal 768 angle, cos minus 20, and this is going to be 768, the sine minus 20. And I'm going to show you in a wee second why we use a conjugate, and it's very handy actually. So 768 times the cos minus 20, 722 say watts, and 768 times the sine 20 minus 262.263 say V8 hours. So we put this here, what we've got is 768 angle minus 20 and 722 watts, and we've got minus 263, but we'll show you what I mean by that. Right, now people say, why do you use a conjugate? What's that? What does that do? Right, if we're looking at, get the light a little bit, our vector kind of graph thing, this is your voltages, L1, L2, L3, yeah? Now, what was this first current? It was, I'm not actually wrote it down, actually, anyway, it doesn't really matter the size of it, because what it was looking like, it was lagging this by 30 degrees, minus 30, right, and this was I1. I2 was lagging this one by 50 degrees, yeah, and that's I2. This one though, mind if that's 120 to this, the horizontal, this was actually leading that one by 20 degrees. Right, so see when you use the conjugate, what the conjugate does is it kind of differentiates the difference between the voltage and whether it's leading or lagging, and it kind of uses it makes, it's kind of like using this, it tells you the difference between the lagging and leading in reference to the actual particular voltage you're looking at, because we're saying that's 170, but we're actually really wanting to know whether it's lagging this or leading it, and this is lagging it by 50, and that's the beauty of the conjugate. When you take the conjugate, it gets the difference between these angles, and therefore you're only looking whether it's leading this, lagging, or whether the current's leading, like it is here. And this is how it helps us to map it into this quadrant here. Right, and what we've got here then, we've got, what we want to do is find out the kind of resultant apparent power we have, the S total. And what we do there then is we just sum all the powers and then sum all the Q's, the reactive powers, and then just treat it like, again, like a Pythagoras triangle. So let's say I'll just quickly do that. Right. So if we add P1, P2 and P3, I'm saying there add P1, P2 and P3, we're going to get this length here, which is 2090. You see that? Yep. And then this is your real part and the total, and the Q total is going to be this one here, 754 VARs of watts. And then we just do Pythagoras again, which is the square root of 754 squared plus 20.90 squared. And that's coming out at 2222 say volt amps. And this angle here is going to be the tan to the minus 1 of this length, the Q over R. So tan to the minus 1 Q over R is going to be 754 divided by 2090. Sorry, that's just a Q a bit. So that's going to be tan to the minus 1 of 754 divided by 2090. And that's going to work out at 19.8 degrees. So that's 19.8 degrees. So yeah, there's one last thing with that star one actually I forgot, is because it's unbalanced, you're going to be having a resulting kind of current that's going to go down the neutral line, and that's you simply just add all the currents together. Use Kirchhoff's law and sum the currents, which I'm quickly going to do now. Just realised I did all this and I wasn't actually recording. Alright, plonker. Right, so because it's unbalanced, there will be a resultant vector or current vector that's going to be going along the neutral line, and what we do to find that is we just simply sum the currents that we worked out previously. So 4.8 at 30, 2.4 at minus 170 and 3.2 at 140. That works out at, remember, cos and sine, cos and sine, cos and sine. So that will be the 4.8 to the cos of 30 is 4.16. 4.8 to the sines of 30 is 2.4. 2.4 the cos of minus 70 minus 2.36. 2.4 the sine of minus 70 is minus 0.42 as I've got there, and again 3.2 at 140 is going to be minus 2.45 plus 2.6. I. So you add all the i's together, you get that, and you add all the j's together, gives you that. Then you use your Pythagoras triangle again. So the magnitude of this is that squared, the square root of that squared plus that squared gives you 3.95, and this angle here, tan to the minus 1 of that divided by that, the 4 divided by the minus 0.065, and that gives you your 73.4 degrees there. Okay, so an unbalanced